You're listening to DTF for June 19th, 2026. I'm your slowly composted host, Jack Haxman. We are your daily tech feed for Hacker News, a website where patience is either a virtue or a bug report. Today's stories reward the ones who stuck around long enough to read the source. Let's get into it. When does patience become a design philosophy? 12 years. That's how long Project Valhalla has been in motion inside OpenJDK. 12 years of mailing list debates, discarded prototypes, and a running joke in the Java community that developers would reach the Norse afterlife before the project shipped. On June 15th, Oracle engineer Lois Fultan confirmed that JEF 401 value classes and objects is targeting JDK 28. The pull request alone touches 1,800 files and adds nearly 200,000 lines of code. It was large enough that other committers were asked to pause their own work during integration. The problem Valhalla solves is architectural, and it dates back to 1995. In Java, almost everything is a reference type. You don't hold a point. You hold a pointer to a point, a slip of paper with a warehouse address. For one object, the cost is invisible. For 1,000,000 objects in an array, you have 1,000,000 slips of paper pointing to 1,000,000 boxes scattered across the heap. Each box carries its own metadata header. Each access risks a cache miss. And modern CPUs are roughly 100 times faster than main memory. So, every cache miss is expensive. The entire performance gap between Java and lower-level languages lives in this indirection. Valhalla's answer is value classes. You write a normal class. Methods, validation, named fields. But the JVM flattens it. No pointer, no header. The data sits in line, packed dense, exactly where the cache wants it. Codes like a class, works like an int. That's been the slogan since day one. What's worth noting is where this work happened. OpenJDK, in the open. 12 years of design documents, public mailing lists, and community review. All of it accessible to anyone who wanted to follow along or push back. Brian Getz published multiple State of Valhalla papers explaining not just what they were building, but why earlier approaches failed. The dead ends are documented alongside the breakthroughs. That's what open development looks like when it's functioning. The blueprints, the mistakes, and the finished product all live in the same place. This is preview in JDK 28, disabled by default. Getz himself called it only the first part of Valhalla. No restriction, value classes, and enhanced primitive support ship now. Generic specialization and full user model primitives come later. The people who said it would never ship will pivot to saying they shipped the wrong part first. That's fine. The code is there. Anyone can read it, run it, and build on it. A $100 billion language ecosystem just made its core memory model substantially more efficient. And every line of the work is public. That's how infrastructure should evolve. Slowly, carefully, and where everyone can see. So what happens when you apply that same obsessive engineering rigor to a database that runs inside your own process? Let's pull this thread. Every analytical database you've used has a dirty secret baked into its architecture. The query finishes. The engine has your results sitting right there in memory, typed and structured, ready to go. And then it throws all of that away. It serializes every value into bytes, shoves them through a TCP socket, and your client on the other end deserializes them back into the exact same types they started as. On a large result set, that round trip, encoding, transmitting, decoding, can take longer than the query itself. You're paying a tax not for computation, but for the privilege of your database running on a different machine. DuckDB refuses to pay that tax, and the way it refuses is architecturally radical. Even though it sounds simple, there is no server. There is no daemon, no port, no wire protocol. DuckDB is a library. You load it into your process the way you'd load NumPy, and when you call a query, the results are already in your address space. A 64-bit integer sitting at a memory address stays at that memory address. Nothing is copied, nothing is serialized. The query result is just there. Now here's where a devil's advocate would push back. Surely the client-server model exists for good reason. Shared access, resource isolation, centralized management. A library database sounds like SOA-Lite for analytics. Cute but limited. Run that argument forward, though, and it falls apart. The workloads DuckDB targets are inherently single-node. A data scientist in a notebook. An ETL pipeline processing a batch. A BI tool rendering a dashboard. These aren't multi-tenant OLTP systems serving thousands of concurrent writes. They're analytical queries where one process needs to scan millions of rows fast. For that pattern, the server is pure overhead. But eliminating the network layer is just the entry point. DuckDB stores data in a columnar format with lightweight compression and zone maps. Metadata that lets the engine skip entire chunks of data without reading them. It processes queries in vectors, not row by row, which means the CPU's cache lines and SIMD instructions actually get used the way hardware engineers intended, and its parallelism model, called morsel-driven execution, divides work into fine-grained chunks that adapt to however many cores you have, with no upfront partitioning. This started as a research project at CWI Amsterdam in 2019. It ships as a single binary under 20 megabytes. The source is open, the extensions are community-driven, and the whole thing installs with pip. Someone ran TPCH at scale factor 100 on an iPhone. An iPhone, the entire codebase is right there. Read it, fork it, build on it. That's how infrastructure earns trust. Open infrastructure you can read and trust. Pause. Next up, MIT researchers took that same philosophy down to the chip itself. One of the top comments on this story is from someone genuinely confused about whether reverse engineering counts as research. Their argument? You're not pushing the boundary of human knowledge. You're just playing a game with other humans who designed the chip. And I want to sit with that for a second because it's a fascinating misunderstanding of what's actually happening here. The MIT team built a custom operating system kernel called Fractal. Not to run applications, not to ship a product, to look at a processor the way a biologist looks at a cell. And what they found is that Apple's M1 chip, which implements an ARM security specification called CSV2 that's supposed to prevent cross-privilege speculation attacks, does in fact block the execute stage. Your user mode code cannot hijack the kernel's indirect branch predictor. Protection works. Spec honored, ship it. Except the chip still fetches the target into the instruction cache before the protection engages. The door is locked, but the doorbell still rings, and you can hear it from outside. That fetch is observable through a side channel. This is the first evidence that phantom-class speculative attacks affect Apple silicon. That's not reverse engineering for sport. That's finding a gap between what a spec promises and what transistors actually do. The reason nobody found this before comes down to tooling. Previous researchers were running experiments on top of Mac OS or Linux, patching kernels by hand. hoping their modifications didn't introduce artifacts. Every measurement was blurred by interrupts, scheduler noise, address space management. Fractal boots on bare metal, with nothing else running, and lets you execute identical instructions on both sides of the privilege boundary in the same address space. The team calls the technique multi-privilege concurrency. It's elegant in the way that only something built for exactly one purpose can be. And here's the part that matters most. Fractal is on GitHub. The paper, the slides, the experiment data, all published. Joseph Ravichandran, the PhD student who led this, dropped the link in the comments himself. Anyone with an M1 can reproduce these findings. Anyone studying ARM speculation on any chip can extend the framework. This is what security research looks like when the instruments are open. You don't need Apple's permission to understand Apple's hardware. You don't need access to proprietary documentation that may or may not accurately describe what the silicon does. You build your own microscope, you point it at the chip, and you publish what you see. The tools exist, the knowledge compounds, and the next researcher starts where you left off instead of rebuilding the same rickety scaffolding from scratch. Full stories in, and we're still finding reasons to be excited. Pause. This next one is a love letter to internet plumbing done right. I've spent more time than I'd like to admit debugging protocol integrations where someone decided a well-known URI was the answer to a problem that didn't need one. You wire up the discovery endpoint, you deploy it, and then 6 months later, someone needs 2 services on the same domain, and the whole thing collapses because you've baked a one-to-one assumption into the architecture. Mark Nottingham, one of the actual authors of the well-known URI spec, just published a piece that reads like a support group letter for everyone who's had to clean up these messes. The core insight is deceptively simple. Well-known URIs solve exactly one problem. Your client already knows the site and needs to learn something about the site as a whole. Robots.txt is the canonical example. A crawler hits a domain, needs the access policy, grabs it from one predictable location. Clean, efficient, done. The trouble starts when protocol designers reach for well-known URIs like they're a credentialing mechanism. Nottingham is bemused and precise about this. Some proposals register a well-known location, expecting it to confer legitimacy, as though a slot in the registry were a credential. It isn't. And then there's the URL shortener pattern, where designers use well-known URIs because they only want to pass around a hostname, instead of a full URL. Convenient today, architectural debt tomorrow. Run this forward. Imagine every protocol that wants discoverability keeps minting well-known URIs. You end up with a root namespace that looks like a junk drawer, which is exactly what the Hacker News comments point out. Someone flags lmms.text to checked as a perfect example of root namespace pollution. Another commenter asks the obvious question: why password reset instead of a generic link tree? Why such granular single-purpose entries instead of composable ones? This is a pattern I recognize from building systems at every scale. The expedient solution. Hard-code the path, skip the indirection, ship it. Becomes a constraint you can't escape later. Nottingham walks through the deployment complications with the patience of someone who has explained this hundreds of times. Scope mismatches between where users interact and where discovery happens. Redirect chains that break assumptions. Sites that don't map neatly onto the services running behind them. What makes this piece worth your time is that it's a protocol designer advocating for restraint in his own protocol. He's not saying well-known URIs are bad. He's saying they solve a specific problem, and if your protocol doesn't have that problem, registering one creates new problems without bringing the adoption you're hoping for. It's the engineering version of knowing when your tool is a hammer and the thing in front of you is not a nail. The spec is open, the registry is public, and the guidance is now written down where anyone designing a protocol can find it before they make the mistake. We talked earlier about tools finding their purpose. Pause. Here's one that found it and ran. 10 years of ClickHouse in open source. In 1993, Linux had 100 contributors. Linus posted the kernel. People sent patches, and the whole thing ran on trust and a mailing list. The conventional wisdom at the time was that serious system software required serious institutions. Bell Labs, Microsoft, IBM, you needed a building and a budget. Linux proved you needed neither. You needed an open repository and a culture that respected the work. ClickHouse just turned 10 in open source, and what Alexei Milovodov has built is the most compelling proof of that thesis since Linux itself. Not because of the database, though the database is extraordinary, but because of how the project operates. Milovodov lays out a taxonomy of open source that's worth internalizing. Level 0 is code you can read museum pieces. Level 1 is public commits, but no outside contributors. A SQLite lives here. Brilliant software, one maintainer, deliberately closed process. Level 3. Matop. Is everything open? Task tracker, roadmap, CI, code review, release cycle, contribution guidelines. ClickHouse operates at level 3, and Milovodov treats that as an engineering requirement, not a marketing strategy. The technical details matter here. ClickHouse started in 2009 as a performance hack, replacing libs Lomstein and mop-stew functions because they were too slow for real-time web analytics pipelines. That instinct, optimizing at the level where most engineers shrug and accept the abstraction, runs through the entire codebase. The project explicitly invites experimental pull requests. Bring a new hash table, a compression algorithm, a sorting method. The CI infrastructure will test it with production-level scrutiny whether or not it ever merges. The repository doubles as a research laboratory for data structures and systems programming. What the community response confirms is that this approach compounds. People replacing Elasticsearch with 5 times better storage efficiency. Teams swapping out timescale DB and finding the experience genuinely pleasant. One commenter nailed it. ClickHouse is the low-key amazing tech people are busy using instead of posting about. Every contributor gets credited in the changelog and in a system table inside the database itself. That's not a gesture. That's architecture. You build the recognition into the system so it can't be removed by a future product manager optimizing for something else. The tools exist. The code is readable. The process is transparent. This is how open source wins. Not by arguing about licenses, but by being so good and so open that the closed alternatives simply stop making sense. Moving on. Someone built Gribouille inside a typesetting language, not as a plugin, not as an external library that shells out to R. As a native, composable grammar of graphics that lives where your documents live. Gribouille 0.3.0 is a plotting library for Typst, and if you've never used Typst, the short version is: imagine if LaTeX were designed today by people who actually like their users. Typst is a modern typesetting system that's open source, compiles in milliseconds, and reads like a programming language instead of a pile of escaped macros. And now it has a real grammar of graphics growing inside it. The question nobody's asking yet: why do we still treat document creation and data visualization as separate workflows? You write your analysis in one tool, generate charts in another. export PNGs, drag them into a third tool, and pray nothing changes upstream. Gribouille collapses that entire pipeline. Your chart is your document. The same type system, the same composition model, the same rendering pass. What impresses me about this release is the craft in the details. Guides and axes now have granular visibility control. You can show a legend for color, but hide it for size, independently. Per aesthetic, the compose function carries its own theme, which means you can build multi-panel figures, where each panel has different styling without fighting a global state. Geom area stacks by default now, which is one of those tiny decisions that reveals someone is actually using their own library and noticing where the friction lives. One commenter called Typst the most important open source project of the last 5 years. That's a big claim, but the argument underneath it is sound. Typst is what happens when you take 30 years of lessons from text and LaTeX and rebuild from scratch with modern language design. And libraries like Gribouille are the proof that the ecosystem is compounding. Once you have a good foundation, people build beautiful things on top of it. The whole stack is open. The typesetting engine, the grammar of graphics, the package registry. Anyone can read it, fork it, extend it. A researcher in Dakar has the same tools as a team at MIT. That's not idealism. That's just good architecture. Now, a sharp turn. We've been celebrating beautiful open tools, but openness has a shadow side, and this one's worth paying attention to. Let's be fair to GitHub for a moment. 500 million repositories. Automated abuse at scale is, by any reasonable measure, an unsolvable moderation problem. You cannot manually review 500 million repos. You cannot build perfect heuristics for every attack vector. The platform is open by design, and openness invites exploitation. That's the cost of doing business. Now, follow that logic to its conclusion. A researcher finds 10,000 repositories distributing Trojan malware. Every one is a clone of a legitimate project. Commits copied wholesale, original contributors listed as if they'd participated. The only modification is a single commit, pushed and deleted and repushed every few hours. Adding a download link to a zip archive containing an executable payload. VirusTotal catches nothing when you submit the link. Only the zip itself triggers detection. The researcher reports it. GitHub support takes a month to respond. Meanwhile, the campaign continues. 10,000 repos. Different usernames. Different project names. No forks. Each one crafted to evade the most basic relationship mapping. One commenter identified the target, and it's worth stating plainly, these repositories are not aimed at human developers. A human would notice the single suspicious commit, the freshly created account, the zip file where source code should be. These repos are aimed at AI agents, coding assistants that search GitHub, pull dependencies, and execute instructions from README files without the skepticism a person would bring. The every few hours repush keeps them surfacing in recent activity queries. Exactly the kind of signal an automated tool would trust. Follow the principle all the way. If your platform hosts 500 million repositories and your response time to a documented pattern scripted attack is measured in weeks, you have not built a platform. You have built infrastructure for distribution and abdicated the engineering required to defend it. The researcher did what the platform should have done. Identified the pattern, wrote the detection script, published the methodology. One person with a hypothesis and API access found what $1 billion company's trust and safety team did not. The tools exist. The knowledge is available. The question is whether the platform treats security as an engineering problem or a support ticket. Now for something entirely different. Story 8. Zen and the Art of Machine Learning Research. There's a line buried in the middle of this essay that deserves more attention than the author gives it. Quote, "The fundamental ideas haven't changed in 40 years. 40 years. That puts us at 1986. Backpropagation had just been formalized by Rumelhart, Hinton, and Williams. Cross-entropy was already old mathematics. Singular value decomposition dates to the 1800s. The tools that power every large language model on Earth today are not new inventions. They are old ideas, finally given enough compute to breathe. This matters because the AI research landscape right now is dominated by a kind of temporal myopia. The essay's author, who works at a major lab, is telling aspiring researchers to stop chasing the vocabulary of 2026. Harnesses, agents, context engineering, and instead go back and compute cross-entropy by hand for a small distribution. Visualize SVD in your head. Understand policy gradients, not because they're trending, but because they've been useful for decades. There is a direct parallel to the Unix era. In 1978, the people who understood pipes, processes, and file descriptors, the actual primitives, were the ones who built lasting systems. The people who chased the application layer without understanding what sat beneath it built things that broke when the abstraction leaked. And abstractions always leak. The essay makes another point worth sitting with. If the best possible outcome of your research is a higher score on an existing benchmark, you are not going deep enough. Benchmarks are closed systems. They define the question and the answer format. They reward optimization within fixed constraints. The most important work happens when someone builds a new way to even ask the question. And that requires the kind of understanding you only get from fundamentals. One of the comments pushes back, arguing that go deeper is a double-edged sword. Fair. But the author isn't saying ignore application. The author is saying that the people who understand the primitives are the ones who recognize which applications matter and which are noise. Suzuki's beginner's mind isn't about ignorance. It is about remaining open to possibilities that expertise has trained you to dismiss. The discipline here is unsexy. Read. Build. Most days, nothing comes. Sit anyway. That is the practice, not the hack, not the shortcut, not the trending framework. The practice. And what does it look like when a community sits with that practice for decades? The Raku Foundation just made it official. How long can a language live in someone else's house before it needs its own dress? Raku just got one. On May 1st, 2026, the Raku Foundation was registered as a stichting in the Netherlands. Registration number 42,050,836. A legal entity. A real address. After a journey that, depending on how you count, started somewhere around the year 2000. There is a concept in mycology called the Wood Wide Web. Trees in a forest share nutrients through underground fungal networks for decades before anyone notices the network exists. The trees look independent. They are not. The network was always there, doing the actual work of keeping the ecosystem alive. Raku has been that fungal network for programming language design. Pattern matching, grammars baked into the language, gradual typing before gradual typing was cool, concurrency primitives that other languages are still reinventing. The organism was alive and productive long before it got a name on a mailbox. One commenter compares this to Nintendo taking 35 years to release a 16-bit Game Boy. And look, the comedy writes itself. Perl 6 was announced in 2000. Renamed to Raku in 2019. Foundation registered in 2026. That is a quarter century from announcement to legal incorporation. Most startups are born, funded, pivoted, acqui-hired, and shut down 3 times in that window. But here is what the joke misses. The foundation is structured as a member-driven organization with annual elections and the -O fun paradigm written into its charter. Fun as a governance principle. They are building democratic infrastructure for a programming language community, compliant with Dutch law, with the explicit goal that contributors of all kinds can participate in decision-making. That is not a punchline. That is open source governance done with actual legal rigor. The Cyber Resilience Act compliance section on their registration page tells you everything about where this is headed. They are not just building a clubhouse. They're building an institution that can navigate European regulatory frameworks. The fungal network finally has a legal name, and it is already handling soil chemistry most projects never think about. We have covered a lot of ground today. Let's close with something that makes the whole AI tooling stack click into place. Every enterprise authentication problem is the same problem wearing a different hat. You have users, you have services. You need to prove that this user should touch that service. The entire identity industry exists because this handshake keeps getting reinvented per application, per protocol, per decade. MCP had the same disease. Every server wanted its own OAuth dance. Every employee clicking through consent screens one by one, connecting tools like it's 2009, and they're authorizing Facebook apps. Security teams watching from the sidelines with no centralized audit trail, no policy enforcement, just a prayer that nobody plugged their personal Gmail into the corporate agent stack. The fix is almost disappointingly obvious. Let the organization's identity provider do what identity providers already do. The new Enterprise Managed Authorization extension hands the IDP a JWT during single sign-on. The MCP server's auth server exchanges it for an access token, and the user never sees a consent screen. Admins define policy once. Users inherit access based on the groups and roles they already have. One login, everything connected. The technical mechanism. Identity assertion JWT authorization grant is a token exchange pattern. The IDP vouches for the user. The MCP server trusts the IDP. Nobody gets redirected through 6 screens to connect a database tool they use every day. The comments are revealing. One developer trying to wire up Entry auth calls themselves an idiot. That's not self-deprecation. That's a symptom. When competent engineers feel stupid using your auth flow, the flow is wrong. The spec is open. The pattern is standard. The real question is whether this becomes the floor that every MCP implementation builds on, or whether it quietly becomes another enterprise upsell checkbox. The architecture is right. The adopters, Anthropic, Microsoft, Okta, have the reach. Now it's a governance question, not a technical one. This has been your daily tech feed for Hacker News for June 19, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7. Voiced by Quen 3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth being patient for. We'll see you back here tomorrow.